Hi everyone, this is Miss Graham, and today we're going to be looking at lesson 25.3, which starts on page 358. We're going to be focusing on angles formed by chords. Let's go ahead and start with our learning targets for today. We're going to describe a relationship among the angles formed by intersecting chords in a circle, and then we're going to use angles formed by chords to solve problems. Chris has been asked to consult on the design of a new soccer Hall of Fame, in which names of former players from his high school are written on tiles around the edge of a circular reflecting pool. The pool has tiles along the inside edges that were designed by art students. For the tiles to have the desired visual effect, they need to be illuminated by spotlights. Students have been submitting their suggestions for the placement of the light fixtures. The light fixtures that are to be used for this project illuminate objects that are within 30 degrees of the center of the bulb. The diagram below represents an overhead view of a single light fixture. Question number 1 asks us, if the light fixtures are placed at the center of a circular pool and aimed outward towards the edge of the pool, how many would be needed to illuminate the entire pool? Let's go ahead and start drawing a picture to visualize this. Let's start off by drawing our circle to represent the pool. Let's add our center point as well. And we want to model what one of these 60-degree lights looks like. So let's say we put the lights in the middle and they were reflecting outwards here. Remember, a whole entire circle is 360 degrees. So if I wanted to model one of those 60-degree lights, it would look just like this. And remember, this is a central angle, so that way it matches up with this part of our circle, the arc of this circle, kind of like the crust to our pizza. So we know this arc also measures 60 degrees. So let's think about how many of these we will need for the whole entire circle. Having our whole circle be 360 degrees, let's say we take 360 degrees and divide it by each of the 60-degree lights. That way we know we're going to need 6 light fixtures. So that way the whole pool will be lit up. Let's go ahead and add each of those fixtures in our drawing here. So we're going to add another 60-degree, another 60-degree light, 60 degrees. And again, your picture doesn't have to be perfect. I know mine isn't, but that's kind of what each of the 60 degrees would look like. We can see that 3 of the light fixtures take up half of the arc of the pool. So we can see it set up that way. Let's go ahead and go on to number 2. If the same light fixtures from question 1 are placed halfway between the center of the pool and the pool's edge and aimed outward, about how much of the pool wall do you think would be illuminated? Estimate the number of additional light fixtures that would need to be illuminating the whole entire pool. Let's go ahead and draw a picture again. Let's start off by drawing our circular pool again. We also want to make our center point right there. Now, remember, we want to place the light fixtures not on this center point, but halfway between the center point and the pool's edge. So what we're really looking to do is we're kind of creating this semicircle, this full circle inside of our big circle. Again, I know this is a sketch, not drawn to accuracy, but we can see that it is about halfway between the center and the pool's edge. So this circle that I drew right here, that's where we're going to be placing our light fixtures. So say we wanted to start off again, placing one of the light fixtures here, drawing that same visual that we had before, where, remember, we're looking at it to be 60 degrees right here. Now, what's going to happen is if we did this completely around the whole entire pool, what actually would happen is only half the wall is going to be illuminated because we moved in half of the distance. So we're going to say about half of the wall would be illuminated. So think of how many additional fixtures would be needed. Well, we would need 6 additional fixtures. We would need to double our number of lights. Now let's move on to question 3. It says, if the light fixtures were placed on the pool edge and now aimed towards the center, how many light fixtures would be needed to illuminate the entire pool? All right, let's go ahead and draw our circle again to represent the pool. Again, we have this center point right here. But now we are taking these lights and putting them on the edge here, not in the middle. So let's think about this. This goes back to what you learned yesterday. Think about if I had a light fixture here, and we know we're visualizing that is a 60-degree angle, and it's opening up this way. Do you see what I'm doing? It's opening up this way. Remember, this 60-degree angle is opening up really to an arc that's going to be twice that measure. So think about this. If the arc is twice that measure, then we know that this arc right here is going to be 120 degrees covered. So we want to see how many light fixtures we're really going to need. So we're really taking 360 degrees, our whole entire measure of our circle, and we're dividing it by 120 degrees for each of the arcs, since that's for each light. When we do that, we get 3. So we know that we're going to need 3 light fixtures. So think about this, right? I could also add these onto our picture. Think about how the rest of the circle is not covered in light. Let's say I wanted to put, I don't know, a light right here. We could see that it would open up to cover one of the other sides that we haven't visualized yet. So we could open it up to 60 degrees. We'll cover this 120-degree measure. Say we wanted to also add the last light fixture. Again, I could put the last light fixture here. We can open it up to our last remaining arc. And again, since this is an inscribed angle, it's 60 degrees, so that way it will open up to be 120 degrees covered of our arc. Chris is considering a design that involves attaching 2 light fixtures back to back and placing the pairs in various locations of the pool. The visual below represents an overhead view of the pool and one of the light fixture pairs located at the center of the pool. Find the degree measure of each of the illuminated portions of the pool. So we're looking at arcs AB and PQ. So think back to 2 days ago when we learned about the angles where their vertex is coming from the center of the circle. Remember, these are central angles. So it's different from an inscribed angle. What we know is if we have a central angle, then we know the arc that it intercepts will also be the same measure. So both arc AB and PQ will equal 60 degrees. As Chris moves the pair of spotlights, point L in the figure below, left to right of the center, he notices that the sizes of the illuminated portions of the pool change. One of the arcs increases in measure. The other arc decreases in measure. So Chris needs to know if there is a relationship between the measures of the vertical angles, X, and the measures of the 2 intercepted arcs, A and B. Part A starts off asking us to draw AP. So we want to add that segment to this circle. So let's go ahead and draw AP. Next, it asks us that each of the angles x is an exterior angle to ALP. So think about this visual. These angles are exterior angles to ALP. So think of how this lines up to be a straight line for 180 degrees. So think about x will equal what two angle measures here. To give you a little bit of a hint, think about what arcs we're really looking at here. So my hint for you was to kind of look at these arc measures of AB and PQ, kind of what we saw before, and see, with our knowledge, maybe looking at what angles open up to those intercepting arcs. And maybe there's some relationship we're going to see. So when we pull this out for arc A, it matches up with angle X, but look where it also matches up, to APB. So it's going to match up to angle measure APB. And now let's think about arc B. Again, it opens up to angle measure X, but it also opens up to angle measure PAQ. So let's add that on in right there. Looking at part C, it says now use the inscribe angle measure theorem to find the measure of angle APB and angle PAQ in terms of A and B. So think back to what we focused on yesterday. Think back to that relationship of how, if we don't have our vertex at the center of our circle, think about the relationship of that angle measure along with the arc. So what we're going to see is the measure of angle APB is going to be equal to half the measure of arc A. Measure of angle PAQ is going to be equal to half the measure of arc B. For part D, it says use your responses in parts B and C to find an expression for X in terms of A and B. So look up above. Look what we wrote down exactly in part B. And let's bring it down here. This idea. So we can see that X equaled those two angle measures added together. So let's do a little substitution of part C and substitute in 1/2 A and 1/2 B and for the angles above. So really X equals 1/2 A plus 1/2 B. Now think about this. If I use, let's say, I don't know, kind of the reverse distributive property, which is really finding the greatest common factor, I could divide out 1/2 from both of those terms. So I could also rewrite X is equal to 1/2 times A plus B. For number 6, it wants us to complete the following theorem with what we know. So think of when two chords intersect inside the circle, in the interior of a circle. So let's add interior in there. Then we know the measure of each angle formed is blank, the sum of the measures of the arc. So think of what word is going to go in that spot. That's right. It's half the sum of the measures of the arcs. Now remember, those arcs are intercepted by the angle and it's vertical angle, just as we saw with X in the previous problem. The theorem in item 6 is also true for an intersecting chord and a secant, and for two intersecting secants. So let's think back to what a secant line is from our last section of learning. Remember, a secant is going to be piercing through a circle. So we have a circle, a secant kind of pierces through the circle. So it'll touch the circle in two spots. Now, for number 7, it says refer to the formula we came up with in number 5. So we're going to look back on what we came up with in 5D. So we came up with the following formula. We said X equals 1/2 A plus 1/2 b, or we could also say it's 1/2 times a plus b. Now it wants us to rewrite the formula for a. So it doesn't really matter which of these parts we look at, that part or that part. I'm going to focus on the second part. So let's think about this formula, x equals 1/2 a plus b. If I wanted to isolate a and get it by itself, think of what would be the process. How do I get rid of timesing by 1/2? Well, you could divide by 1/2, or think about how you could just times by 2 to each sides. Because timesing by 1/2 and timesing by 2, really those are kind of looking at keeping our value the same, inverse operations. So now we're going to have 2x equals a plus b. And the next step to get a by itself would be to subtract b. So lo and behold, we have 2x minus b equals a. And that's looking at our formula, saying, hey, let's imagine I have one of the arcs that I'm looking for. I could take 2 times the value of the vertical angles and subtract out the other arc to find that second arc. Chris decided that he liked the effect when the back-to-back light fixture pairs were placed off-center because some of the tiles would be lit up more brightly than others. In the figure below, point A represents the location of a pair of the spotlights, and the arcs WX and YZ represents the parts of the pool edge illuminated by the spotlights. Recall that the measure of WAX is 60 degrees, so let's throw that back into our picture. So this angle measure is 60 degrees. And also think about how this side will also be 60 degrees. They give us the measure of arc, WX. So the measure of this arc right there is 100 degrees. It wants us to use kind of that equation that we came up with before to solve now for the measure of that other arc, ZY. So think back to that formula that we came up with before. We could use the general one that we had before we manipulated to find A. So we could use this formula of x equals 1/2 times a plus b, and then plug in, our angle measure, your vertical angle, x is 60. Plug in 100 for A and B and solve for the other one. Or we could use that isolated equation we just came up with in our last problem, where A equaled 2x minus b. That might be a little easier to work with since A is already isolated for us to find YZ. All right, so let's plug in what we know. So A will be equal to 2 times x, where x is in 100. It's going to be the 60-degree angle, the vertical angle. And then we're subtracting out our b, which is that other arc, 100. So 2 times 60 is 120. 120 minus 100 gives us 20 degrees. So looking at this, we're going to see the measure of the missing arc is going to be 20 degrees. Looking at part B, it's now asking us to add together the measures of arc WX and YZ. So think about what we just found. We just found YZ was 20 degrees. And we had that 100 degrees from before. So when we add those two together, we get 120 degrees. This verifies our formula from before that we really want to add together the measures of the two arcs and take half of this value, and it'll give us our vertical angle, which it works. Half of 120 is 60. Now let's say for part C, we have the measure of WX. We know that arc is 100 degrees. Then which arc in the figure will represent the part of the pool's edge where the tiles are most brightly lit? So what they're asking us to do is to compare those two arcs, WX and YZ, and see which one of them will light up the tiles that they are facing more brightly. Well, think about this. We know why Z, that arc, will light up them more brightly since we know the light is closer to that arc. So since the light is closer to that arc. All right, we are finally on our last problem for today, number 9. So, in his design for the reflecting pool, Chris placed 3 of the back-to-back light fixture pairs as depicted in the figure below. So, looks a little complicated, but no worries. We see points A, B, and C. They represent the location of each pair of light fixtures. Each pair of light fixtures is equidistant from the center of the circle. So what that means is we have ES, that arc, is equal to IG, is equal to the other arc, DN. So question A is asking us, will the entire pool edge be illuminated in this diagram? And to explain, let's think back to this idea of intercepting arcs. So going back to, let's say, light fixture A, we know that it's going to open up to this arc right there. We also need to remember that since the fixtures are back to back, it is also going to open up to that arc right there. Let's say we wanted to go into light fixture B. We can see is going to cover arc ES and NG. Last but not least, let's go to light fixture C. Remember, since they're back-to-back light fixtures, it'll open up and cover DN as well as arc IS. Therefore, we can see that all of these light fixtures cover the entire circle. So the intercepted arcs make up the circle. So let's write that down. So we're going to say yes, the intercepted arcs make up the entire circle. Looking at part B, it now says shade in the region of the pool that will be illuminated by more than one spotlight. So it's not necessarily the circle that's here. Think about inside. What areas will be illuminated by more than one spotlight? Wouldn't it be this area inside here, since all of these lights are facing each other? Yeah, it would. All right, part C says, if arc ES, so right here, it's going to be 1/4 of the circumference of the pool, then it's asking us what is the measure of arc DE. So think about this. We want to figure out what is 1/4 of 360. We're really looking at 360 and dividing it by 4 or timesing it by 1/4. When we do that, we get 90 degrees. So we can see that this arc is 90 degrees right there. Now, thinking about this, that means the other larger arcs, like GI, that's also 90 degrees. And DN, that is also 90 degrees. So I want to figure out what these last pieces are here. Think about if we took all of those 90s, added them together, or really timesed it by 3, it would be 270. And we're really looking at taking 360, our whole measure, subtracting out 270 to see what the measures of the arcs that are left. When we do that, it's 90 degrees. So we're taking that 90 degrees from right here and dividing it by 3 to represent arc DE, SI, and NG, because we just want one of those arcs. So lo and behold, we're going to see that each of these smaller, tiny little arcs will be 30 degrees. So to answer the question, what is the measure of arc DE? It will be 30 degrees. Our last question is really a critical thinking question. It's now asking what fraction of the pool's edge will be in the brighter light from the rest of the pool's ledge. So think about if the larger arc or the smaller arc will be more brightly lit. I mean, it's definitely going to be the smaller arc because the light fixture is closer to it. So we're really looking at all three of these pieces right here, all of those smaller arcs, the 30, 30, 30. So really, we're taking 90 degrees and dividing it by our whole. We're taking the part divided by the whole, which is 360. So think about this. When we reduce that, that gives us 1/4. So 1/4 of the pool will be brighter and light than the rest of the pool's edge. Good news, there is no homework tonight, but keep in mind everything you've been learning about angles and arcs this week will be coming back into play when we come into class tomorrow. Have a good day and happy mathing.